done with Python over the years. I want to start off though talking about something called paralipsis. Paralipsis is a rhetorical technique where you mention something by saying that you're not going to mention it. Politicians do it all the time when they say, I'm not even going to mention my opponent's alleged infidelities. Another example would be, in this talk I'm not going to mention the fact that I work for a company called Eldarian that does web consulting. I'm not going to mention the fact that we provide Django and Python hosting in the form of Gondor, and I'm not going to mention that we run a habit tracking site called Habitualist. I'm not going to mention any of those things. Not only did I not mention them, but I actually technically didn't make a paralipsis. I just gave you an example of what a paralipsis was. So I guess it's a better paralipsis. All of the stuff that I'm going to be talking about is open source. It's available on GitHub, so I encourage you to check it out later. I'm around for the entire conference. I'd love to talk to you more about the various projects that I'm going to be talking about. And of course, the obligatory, please follow me on Twitter. So I've entitled this talk, You Used Python for What? But it really should be, you are using Python for what? Because most of the things that I'm going to be talking about are ongoing projects that I'm still working on. Many of them are works in progress. They'll have varying degrees of usefulness. Some of them I think are useful. Some of them I'm sure you'll all agree are pretty useless, but hopefully fun nevertheless. I'm going to be talking about implementing a language called brainfuck in Python, church encoding. I'm going to talk about Git-like data structures, analyzing piano performances, doing graded readers for advanced Greek, writing operating systems in Python, and then finally emulating the Apple II. So my primary goal here is that you find at least one of these interesting. My secondary goal is that you question my sanity. Some of the stuff is a little weird. But at the heart of, I guess, everything that I'm going to be talking about is the fact that, for me, I don't really understand something unless I can implement it in Python. And Python, for me, is a great way of diving into something and really getting into making sure I understand at least a little bit about it, enough to do an implementation. Richard Feynman, the famous American physicist, this is a photograph of what his blackboard in his office looked like when he died. And you'll see that, you probably can't make it out, but in the top left corner, he's got written, "What I cannot create, I do not understand." So it's the same kind of sentiment, that there's an incredible understanding you can gain from actually being able to create something in the context of this talk, what you can implement in Python. So let's start off with a language called brainfuck. Brainfuck is what gets described as an esoteric language. It's sort of used to prove a point more than to actually be useful in any real way. There's only 8 commands in brainfuck, each represented by a single character. And it's a Turing complete language. So any algorithm that's computable can be implemented in brainfuck. But the basic way it works, it's a Harvard architecture, so you separate your data and your program. You've got data and you've got a pointer keeping track of where you are in your data. You've got your program, which is just made up of these characters, and you keep track of where you are in the program. And you just continually execute commands. You've got a command for incrementing the data pointer, one memory address across, one memory address back. You can increment or decrement the value at that location that the data pointer is pointing at. There's a bit of I/O. You can output the byte that you're currently pointing to as an ASCII character, or you can read in an ASCII character and put it in the memory location you're pointing to. The kind of conditional logic is that you have these square brackets where if the data pointer is 0, pointing to a 0, then you skip over the bracketed section. Otherwise, you go through the bracketed section and loop back until that 0 condition is met. And that's enough to be Turing complete. So, anyone know what this program does? Any guesses? Hello world, exactly. So this outputs hello world. To give you a flavor of how this works, does anyone know offhand what the ASCII character for the uppercase H is? Think about it. 72. Now 72 is 9 times 8. And you'll notice at the top, we've got 9 pluses and then 8 pluses. What's basically going on is we're moving across one, incrementing it to 9, going back, adding 8, and then going forward, decrementing the 9, going back, adding another 8. So it's a quick way of basically, that first line is adding 9 8 times so that you get 72, and then you're outputting the H. So that first line is outputting the H, the next line is outputting the E, and so on. You can see the double L is easy because you've just got a dot. You've already got the ASCII character at the data pointer. So what does it look like in Python? You know, I read about this thing and I thought I want to play with this, I've got to implement it in Python. So really, really simple program. I've just got 64K of memory, I've got a data pointer P, a program counter PC, and then I've got my actual program. And I just loop through. Most of these are really, really simple. You can see I'm either incrementing the memory location, the data at the memory location, I'm incrementing the data pointer, I'm reading or writing. The only one that's a little more advanced is the square bracket. Basically, when I hit a square bracket, I work out where the matching closed square bracket is, and of course they can embed, so I have to keep track of how deep I am to know where I find the actual matching square bracket. And then I just execute that if the data pointer is pointing to a non-zero. And that's it. This is an example of a program that takes 2 numbers, and as long as the answer is a single digit, will output that. It's kind of similar to the way that the hello world works. The way this works is it takes an input, that's what the comma does, and then it basically, instead of adding 72 like we saw before, this subtracts 48. I think it's 48. 6 times 8, that looks right. Or 6 times 7. What that's basically doing is converting an ASCII character to its actual numerical value. So if you type in 3, the ASCII character for 3 is 51 or whatever, so you subtract 48, you get the 3. Then you read the next number. You don't bother subtracting off the 48 from that because you want to add back the 48 to know what to print. So it just adds the second number that you type in and then outputs it. And that's it for brainfuck. Completely useless, but a lot of fun. That was an interpreter. One of the things that I haven't done, but may do at some stage, is maybe write a compiler to compile brainfuck. Maybe into Python, which would be really weird using Python as a target for a compiler, but certainly possible. Church encoding is a lot of fun. Church encoding was partly developed by Alonzo Church back in the day, where they were exploring the whole notion of computability and the lambda calculus and so on. The basic idea of church encoding is that you can represent various things purely in terms of calling functions. And I don't mean calling functions on data, I mean the data actually is just a function that calls other functions. And there's nothing more to it than that. So in a weird way, this seems strange at first, but bear with me because it actually kind of works. If you define true to be a function that takes A and returns a function that takes B and returns A, and you define false to be a function that takes A and returns a function that takes B and returns B, it may seem odd that you would do that, but you'll see on the next slide why that's actually, that actually works out. But for now, just to kind of give you a little indication of how this is working, if you've got one of these church encoded booleans, you can pass it true then false, and it will spit out whichever one it is in Python. So if you've got something and you're not sure if it's one of these church encoded trues or you're not sure if it's one of these church encoded falses, you can always pass it true. It'll return a function that you then pass false, and whatever it spits out will give you a Python boolean. So not useful yet, but that's how we can go from the church encoded world to the Python world. However, what you can now do is if you define and, or, and not in terms of these various functions, then it actually works. You can do and, true, and false, and it will return false. Now, of course, what it's actually returning is just another function. We're never dealing with any data whatsoever. This is all, we're just passing around functions. So we need to do this trick at the end to convert it from the church encoded world into the Python world. But you're able to do Boolean logic just in terms of these lambda functions that do nothing other than return other lambda functions. Now, those of you who've done any kind of Lisp or scheme will be familiar with cons, car, and coulda. Normally, the way cons is talked about is it's how you make a pair data structure out of two objects. Cons takes two objects and basically returns a pair. But if you've read anything like the structure and interpretation of computer programming or any of those kinds of very Lisp or scheme heavy books, you'll know that another way of thinking about it is cons isn't necessarily building a data structure of a pair. What it's building is something that if you call car on it, it'll return the first item, and if you call coulda on it, it returns the second item. How you actually implement that data structure doesn't matter. And that's at the core of what's going on here. Cons, again, isn't actually building any pair. It's just functions calling other functions. And car and coulda can be defined based on true and false. And now we're able to actually use car and coulda on something that is constructed with cons. So you can see if you call car on a cons of 1 and 2, you get 1. If you call coulda on a cons of 1 and 2, you get 2. Now that definition of cons actually helps us out a little bit with unchurching these booleans. To go from the church encoding world to the Python world, you can always just call cons on something and it will have the same effect of calling true and false to find out whether what you've got is a true or false. So if you want to really find out whether not true is, what the value of not true is, you can unchurch it to get false, and similarly with or, true and false will return the right answer. Now, if all you could do with this was Boolean logic, it might be a little dull, but it turns out you can actually do arithmetic with this too. And just another reminder, there's no numbers here. We're not, in the Python implementation, no numbers appear anywhere, no additions, multiplications, exponentiation happens. We're just purely using lambda. So first of all, how we define the numbers. We define 0 to be false, and we define this function successor, succ. It's a function that takes a number and returns a a function that takes something and returns a function that takes something, which returns a function that takes something, and it applies the second thing to the application of the first thing to the second thing to the third thing. You can see the definition there. Kind of weird, but it works. You can then define 1 as the successor to 0, 2 as the successor to 1, and so on. And just a little Python helper function there for actually how you can church an arbitrary number. It's just a recursive definition there. 5 is just the successor of 4, which is the successor of 3, and so on, until you get back down to 0, in which case it's defined as false. Now this is the really crazy thing. You can define plus, multiplication, or addition, multiplication, and exponentiation. And what's kind of cute about this is that exponentiation actually ends up being the simplest. And it's easier than multiplication, which is in turn easier than plus. But this all works. Obviously, once we've done this, we need a way of extracting out from our crazy church encoded world back into the Python world to make sure we got the right answer. So here's a little function that actually calculates the number back out. And this works. You can unchurch the numbers, you can add them, multiply them, do exponentiation. So again, something I'd read about in Wikipedia, various books and stuff like that. Wanted to try it out for myself. The way I did it was to implement it in Python. Okay, Now we're getting into perhaps a little more practical stuff. When I was first learning Git, of course I had a bit of a mind melt at first. But as I started to understand more about the underlying data structures and the way that it worked, it actually started to make sense. But of course, I needed to implement it in Python to really understand it. And I'm not talking about implementing Git in Python in the sense of an actual Python implementation of Git, but rather exploring the underlying way in which Git works in Python. So at a very fundamental level, the way Git works, for those of you who haven't dug under the covers, although you're pretty much forced to dive under the covers a little bit with Git. Every file's contents is hashed, and that hash is then used as a key into a dictionary of that content. So if two files have exactly the same content, they'll have exactly the same hash, they'll only effectively get stored once. Then each directory on your file system that you've put into Git is viewed as a sorted list of file names paired with whatever the hash of its contents was. And then the directory listing itself can just be hashed. It has a textual representation which can be hashed, and then that becomes the hash that you would use for subdirectories and so on. So an entire tree can just be basically built up by a dictionary of these hashes that have the actual content, or directories that themselves just contain references to those hashes. And then when you actually commit something, it's just a combination of the hash of the overall tree, the commit message, who the committer was, the timestamp, and whatever the parent or parents were. If it's a merge, you've got two parents. If it's just a normal commit, you've got one parent. If it's the very first commit on a repo, you've got no parents. It occurred to me when I was exploring this that files and directories, as I just described them, are kind of a lot like strings and dictionaries in Python. And that led me down this path of, well, rather than implement these Git ideas assuming we've got files and directories, why not do it with arbitrary Python data structures? Why couldn't you hash lists and tuples and dictionaries, and they be the things that you're actually building this Git Git version control system around. So this is the part of the implementation. I've basically got a repo. It's got a dictionary of objects. The way that objects get stored is you basically take a SHA-1 hash of the byte representation of that object, and I'll show you in a moment how you get a byte representation of an arbitrary object, and then you store that away. So the basic way that the byte generation works, there's a base class called node base, and in the very simple case, it just takes whatever the content is of the data structure that you're talking about and returns that. So a list, it's sort of recursive. So if you're just dealing with an atom like a string or a number, you can just very easily take a SHA of that. If you've got something like a list, you actually want to take each item in the list, calculate the SHA of that, then what you end up with is a list of SHAs that you can then hash to get a SHA for that list. And the same applies to dictionaries and tuples. When you want to expand something, you can just, there's a method on the repo, you just give it a SHA, it looks up the object and recursively expands it. I won't necessarily go into a huge amount of detail with this, but this is showing how you actually do a commit. Just in the second part, you pass in an object, you shrink it. In other words, you recursively SHA all the components of it and put those in the store. You find out what the previous head was. You make the commit with the old head as a parent, and then you move the head to the new SHA. And you can do branching as well. Some of the future plans I have for this is, first of all, more object types and representations. You can't do arbitrary Python objects yet, only the core data structures. merging and diffing, I think, will kind of be interesting to be able to do diffs between Python data structures, to be able to say here's two dictionaries of lists and I want to see what the differences between those are. And something I've just started working on is remotes, which also might be another interesting way of efficiently exchanging partial Python data structures between devices. Git is a great way of, if you've got two repositories, working out what you need to send one repository to make sure that the two of you are in sync. This will apply here, where if you've got some Python data structure on one machine, Python data structure on another, you want to work out what you're going to need to send minimally to make sure that both are in sync. I think this is going to be an interesting approach. So a little crazy, but potentially useful in some applications. And of course, with no irony intended, well, it's not really ironic, it's obvious that this stuff is all on GitHub. Okay, moving on to something that's a little more domain specific, I guess. A project called Cherney, which is about analysing keyboard performances, mostly piano performances. So the basic idea behind Cherney is that you record somebody playing a piece of music. You don't record the audio, you record the MIDI, so you're getting data about what notes they pressed when and how hard. The goal of this is less about a general performance of a piece, more about, at least in the short term, more about various piano exercises that people do. So if somebody's doing scales or they're doing some exercise by Cherney, the namesake of the project, or Hannon, or any of those sort of standard piano exercises, the idea is that you record the MIDI of somebody playing it. You then align the notes that they played with the notes in the score, and I'll talk about that in a moment. And then you can identify errors where they played the wrong note, or there were fluctuations in timing or velocity, or there was uneven playing. You can basically do a diff between what they played and what they should have played. So again, we don't need to go into the details of this, but basically there's a very famous set of piano exercises by a guy called Hannon, and this is just some Python code that generates the score, if you like, of one of those exercises. Basically, what it outputs is two numbers. One's a note, and the other's how long the note gets played for. Right, so this is kind of our score for purposes of this project. Play note number 48 for, in this case, a semiquaver is what 4 means. Now the way that I actually record the performance, I use Python talking to core MIDI on a Mac, but you could, I've got code for also actually just reading in MIDI files and so on. But really, really simple. You run this Python program, it's listening on core MIDI, you play, and what gets spit out here is something like this. So this is actually me performing that Hannon exercise. The first number is the time that I played the note, the second number is what note I played, and the third one is how hard I pressed down the note. Then the next task is to basically align those two, to match, because I may not have played every single note. The number of notes I played may not have been the same number of notes in the score. I might have played some notes twice. I may have got them slightly wrong. But we basically need to align the two. And so the algorithm that I played around with was the Needleman-Wunsch algorithm for doing string alignment. So this is exactly the same sort of thing that you do in a diffing algorithm when you're comparing code. It's similar to the sort of stuff that gets done in DNA sequencing when you're trying to match up sequences. But in this case, what I'm trying to match up is notes in a score with notes that were performed on the keyboard. And the way that all these, or most of these, linear programming based alignment algorithms work is you have some notion of a score that you give a match. The higher the score, the better the match is. So if somebody plays exactly the right note at exactly the right time and with exactly the right velocity, you give it a high score. If they play completely the wrong note, then you give it a low score. And this is something that I'm still exploring, but this is basically the way I do it at the moment. I don't worry about velocity or duration. I'm just purely looking at what note they hit. If they get exactly the right note, it's a 1. If they are off by a semitone or a tone, they get half. Otherwise, it returns 0. And using this with the Needleman-Wunsch algorithm basically does an alignment. And then once you've got the alignment, you can easily identify which ones did they get right, which ones did they get wrong. So the sort of next steps that I want to take from there, actually visualizing the results. So one of the things I want to do is there's an open source music score generating software called LilyPond. What I would love to do is actually then go back and annotate the score, color code it maybe with what notes the person got right or wrong. Be interesting once I annotate scores with what finger you were supposed to play with it, doing things like identifying whether particular fingers are deficient versus others. It's a common thing in piano that you know, the 2 outside fingers are much weaker than the rest, and so they tend to play lighter, they tend to play a little off time. This would be a fun way of actually quantitatively measuring that. And also be able to grade performances. Also study expression, because it's an important part in performance that you're not necessarily playing exactly the way the score said. Right? The whole notion of expression in playing music is sometimes you do play it a little slower, a little faster, a little louder, a little softer. But by being able to align the score with the performance, you can actually start to get a sense of what are they doing, is the performer doing that in a systematic way. This actually led really nicely into, I don't know how many of you are familiar with something called the Open Goldberg project, or how many of you are familiar with Bach's Goldberg variations. Very famous piece of keyboard music by Johann Sebastian Bach. Some would say possibly the greatest piece of music ever written is something called the Goldberg variations. Basically, it's a theme, a 32-bar theme, and then a series of variations that basically explore all sorts of ideas in music just based around this one theme. There's been a project over the last couple of years, I think it's been running for, called the Open Goldberg project, to basically produce a completely open edition of Bach's work, you know, the score, being put under a Creative Commons license, getting a professional pianist to perform it and record it in a professional studio with a professional producer, make the audio available under a Creative Commons license, and so on. So a fantastic project. The score and the audio files were released just a couple of months ago. And if you're interested in any way in that sort of music, I definitely recommend you check out the Open Goldberg project. But one of the things that they talked about when I first announced the project was that they were going to be recording it on a particular type of Bosendorfer piano that stored the information about what notes were pressed when and how hard. Right? Bosendorfer makes, Yamaha do too, make these grand pianos that actually have sensors on the hammers, and they can actually write to disk exactly what was pressed when. And so the promise was that not only would this project produce the audio files, but there would actually be this computer readable representation of the performance that could be used for people like me to play around with things like Czerny. And you'd be also able to generate a MIDI file from some. You know, I wrote to the organisers, because when they announced that the audio file had come out, I'm like, I don't see the MIDI files, I don't see anything coming from this Bosendorfer piano. And the organiser wrote to me and said, yeah, that's going to take months for us to clean up. And I'm like, okay, is there anything I can do to help? Because you know, I'd been working on this Czerny project, and he sent me the raw files. He said, here's the dump of what came out of the piano. And this is what it looked like. And I went looking on the internet for any information about these BOE files, nothing. So I stared at this for a while. This was kind of my, you know, John Nash beautiful mind moment, I guess. These things started to, I don't know if you can notice, right? So The first thing you start to notice here is the recurrence of an FF every once in a while. Sorry? Yep. It's not always a null if you keep going, but yes, it is followed by a null at the start. The other thing you notice is that actually the first 3 bytes after the FF are monotonically increasing, often just by 2. So after the first FF, you've got 007AC6. After the second FF, you've got 007AC8, and so on. And I started thinking, I'm wondering if that's a timestamp. And because I was able to look through all the files to make sure this pattern turned out, and sure enough, it was monotonically increasing not only within a file, but actually between files as well. And then that leaves what follows. And in this case, there's always 2 bytes, I think, after the 3 bytes that we suspect are the timestamp. But as you go further down in the file, sometimes it's more than 2. It's always an even number, though. So my theory was, well, maybe that's a pair of what note's being pressed and how hard is it being pressed. So I extracted out, and the idea was that if you had more than 2 bytes after the timestamp, then maybe 2 notes were being pressed or 3 notes were being pressed. So I extracted the first out of each pair and did a histogram of how often they occurred. And sure enough, for a piece that was in G major, the most common thing was, they tended to be, the most common values were spaced by 12 and so on. So I was able to eventually work out that those numbers are what key's being pressed, and that what follows is the pressure that the note's being pressed at. So I'm now in the process of, I've written some preliminary stuff to actually extract MIDI files out of this data. One of the challenges, so there's 2 challenges that really exist here. One is that MIDI does things a little differently. With MIDI, you only record when the note is hit, and you just record how hard it was hit. There's a lot more information here because it's basically recording how much pressure is on the key at every 2 milliseconds. So it's not the velocity, it's actually the distance, if you like, of how far the key's being pushed down. So I've been trying to work out all these sort of heuristics for how you translate the location of the hammer to a MIDI velocity. And I haven't quite got it right. We don't have time for me to play you a result, but I'm around all weekend, so if you're interested in hearing a result. Sometimes I pick up stray notes, sometimes the note doesn't quite come out right. But the organisers are thrilled because they've basically said, we don't need to do anything now, you've taken this pressure off us. But I mentioned there were 2 challenges. The first challenge was sort of how on earth we map this to something like MIDI. The second challenge is that these are raw files. So this isn't the performance that you hear. This is every single take, every single, I played for 10 seconds and made a mistake and I went back from the start. So I'm currently talking to the organisers of the project about, well, can you give me the notes from the producer that said, we use take 37 of this or whatever, because otherwise I've got hundreds and hundreds of performances of the Goldberg variations, and I don't know which the one that they have deemed the official one to be. Anyway, that's more fun with Python. A few more things. I'm going to have to be quite quick here, so I'll be very quick around this one in particular, because I really want to get to the Apple II stuff. So the basic idea of this work, the graded reader generation, is if you're trying to learn a language to read a particular text, maybe you're wanting to read ancient Greek philosophers or the New Testament or some Tibetan scripture or something, and so your primary focus of learning the language is to be able to read the text. Is there a way in which you can structure the order in which you learn things to be able to read the text more easily? One of the things that often gets, so in other words, from a real text, extract a graded reader, where you're sort of shown an easy sentence first and then increasingly harder text, building on what you've already seen from previous sentences. One of the things that gets thrown around, unfortunately, when people are learning languages to read a particular text is they'll get told stuff like, well, if you only learn the 10 most common words, you'll be able to read 37% of the text. Because it's true that the 10 most common words in a text probably do account for 37% of the text. But if the only parts of Shakespeare you could understand were the, and, then you're not really going to get the gist of the story. And the 100 most common words are supposed to account for 66% of the text, but unfortunately it turns out that often the words that you actually need to know aren't one of those 100 most common. Another way of looking at it, and these numbers, by the way, are all based on the Greek New Testament, which is the primary focus of my work in this area. If you learn the top 100 words, there's actually only, you'll be able to understand one word in 99.9% of verses. So in almost every single verse, you'll be able to recognise at least one word. It's probably going to be and or the, or something like that, right? But reading theorists say that reading comprehension really requires you to have on the order of 95% coverage. So in other words, if you learn the top 100 words, you won't have 66% of the text, you'll have 0.6% of the text in terms of really actually being able to understand the verse. So frequency ordering is not a great way of doing it. In fact, you can, well, I mean, I think it's the case actually that if you, well, if you learn the first 100 words, you'll only be able to understand just that small fraction. So the part of the problem is, there's a number of problems. Part of the problem is that sometimes a verse will just contain one word that's unusually rare. And if you only knew that word, you'd be able to read a lot more. So frequency ordering is far from optimal. It turns out, though, that trying to work out what the optimal ordering would be is equivalent to the travelling salesman problem. And so you can't just generate all possible orderings of vocabulary and see which one's the most efficient. So I played around with some simulated annealing, and I'm not going to go through this in the interest of time, but basically implementing simulated annealing. Simulated annealing is basically this idea that you go through randomly picking pairs and swap them. But you want to avoid getting caught in local optimizations and missing the global optimization. Sometimes you allow a swap that actually takes you in the wrong direction. So if you find a swapping this word with this word increases the results, then that's good. If it decreases the results, you sometimes allow it. But what you do is you allow a lot more of those kind of bad swaps at the start, and as it cools down, hence the term annealing, you allow fewer and fewer. So you let things bounce around a lot at the start. So if you get caught in a local maximum, there's a chance that you'll get bounced out. But as things cool down, you get closer. I'll briefly talk about CLEASE. The idea of CLEASE is to run the Python VM on bare metal. So basically remove the parts of CPython that assume there's an operating system underneath, and let Python directly talk to I/O ports and memory. And then you can even write your device drivers and so on in Python. So this is a little bit of C, not Python, but this is sort of typical of the way that things get implemented in CPython. In this case, actually implementing two new built-ins, in B and out B, for writing bytes to I/O ports. So this is basically the implementation of out B, and then you can implement a speaker driver in Python by basically being able to write to I/O ports on an x86 machine. Similarly with the keyboard driver, you can get scan codes by directly accessing ports. Now, CLEASE is still a work in progress, but it does work. The sort of the proof of concept has been proven out. There's two approaches that I've taken, neither of which I'm completely happy with, and I keep switching my mind back of which is the better approach. One is you start with CPython and remove the bits that get in the way. The other is you start with nothing and just add the bits of CPython you need. It's a hair-raising project, but a lot of fun. I learned a lot about the internals of Python doing this. There's no proper memory management yet, so the thing crashes once it can't allocate any more memory. I would love to explore more this notion of a task-specific subsetting of CPython. So if you don't need certain bits of CPython, they don't. You basically you can almost imagine sort of coverage testing and saying, okay, well, we don't need these bits, and then gradually add them back in. So we're doing less of that subsetting. And I definitely want to explore using PyPy rather than CPython, because I think that'll make it a lot easier to extract out the bits of CPython that assume there's libc underneath, that there's an operating system underneath. Okay, I do want to finish off with the Apple Pi emulator. As Eric mentioned, I've been a 6502 fan for a long time. And Apple Pi is a fully working Apple II emulator written in Python, and I'll show you it in a moment. But basically, all the various opcodes get implemented in Python. You can do memory addressing, taking into account how many cycles get taken to read the next word from the program counter and so on. This is how LDA is implemented, load into the accumulator. Whenever you do various operations, you've got to update the 0 flag and the sign flag. All this sort of stuff gets implemented in Python. And then, of course, you have the soft switches. Those of you who are familiar with the Apple II, the way that you interacted with the I/O is that there was a range of memory where if you read that bit of memory, it would trigger something on some peripheral. So you could start the disk drive motor by reading a particular part of memory. You could make the speaker oscillate once by reading a particular bit of memory. And so obviously what I have to do is listen in for any accesses to that range of memory and then translate that to whatever the equivalent is. Some of the real challenges in this, obviously the character generation, actually drawing the letters properly. The cassette interface was kind of tricky because I'm basically getting an audio file and I'm having to poll it as if the Apple II is listening in, and it's sort of doing a flip-flop of when it thinks, and depending on the frequency of the flip-flopping, whether it's a 0 or a 1. The speaker was particularly weird, because you've got this weird situation where it's really easy in Python to say, oscillate the speaker at this frequency. But that's not what the Apple II is telling me. The Apple II is telling me, oscillate it now, oscillate it now, oscillate it now, oscillate it now. And so what I actually have to do is keep a buffer of whenever it tells me to oscillate, I record what time it told me to oscillate, what time it told me to oscillate. And then a little bit later, imperceptibly later, I say, well, I notice it's telling me to oscillate every 440 times a second. So now I'm going to go play a 440 hertz note. Graphics is particularly tough as well, because if any of you are familiar with what Steve Wozniak had to do to get color graphics on the Apple II, there's all kinds of wacky tricks with NTSC that he did where, depending on whether you're on an odd or even scan line, depending on whether you're writing to an odd or even byte, you got a different color. And of course, from the point of view of the implementation, when I'm implementing it in Pygame, all I want to know is, do I do that dot purple or green or orange or whatever? But that's not what the Apple II is telling me. Right? The Apple II is telling me this weird thing. It's this weird impedance mismatch where the programmer of the Apple II says, I want to put an orange dot there. The operating system works out, well, to get an orange dot there, I need to work out if I'm on an odd or even scan line, and I need to shift these bits this way and so on. And then the emulator has to then work out, oh, that means he just wants an orange dot there. So there is that same with the disk, which I haven't quite implemented yet, right? The programmer says, I want to move from track 3 to track 4. The operating system says, okay, well, in order to do that, I'm going to need to fire this magnet at this point, and then wait this number of milliseconds and stop the magnet. So the stepper motor moves just over. And then I need to translate that back to, okay, we're moving from track 3 to track 4. I will quickly show a demo at the end, but I will get through these slides first. One fun thing, Notch, the creator of Minecraft, is working on a new game that will have a processor in it that you can code. And it's actually similar to similar to a 6502, that kind of era of processor. And so when he published his specs, first thing I did is, of course, go and implement it in Python. So there's an implementation of Notch's DCP-U16 as well. It's available on GitHub. A couple of other things I've worked on. An iterated function system that generates graphics like this. A global illumination renderer, which is kind of a more advanced version of ray tracing. Those of you who are familiar with ray tracing will recognize this as a Cornell box. These kind of things, by the way, you really start to appreciate the speed of PyPy. You get about a 50x increase in speed running these in PyPy. And any Ultima 4 players here? Anyone here played Ultima 4? Oh, young crowd. Well, a couple of people are nodding their heads. So something I did, I remember doing this on the Apple II, but I went back and did it again recently with Python. This is the world map of, it's actually a 4096 by 4096 image. So with Python, I extracted out the individual tiles, extracted out the world map, and then generated this PNG. A bunch of other stuff that I've worked on, none of which I'm going to talk about here, but as I said, I'm here all week. As I said, all this stuff's on GitHub. That's me on Twitter. If you want to support this, I strongly recommend you check out GitTip to support not only me, but other people working on crazy things like this. Tad's here if you want to talk to him more about GitTip. I just want to finish off because I have to demo this just to prove that it does work. The Apple Pie. Let me turn up my speaker. I don't know if you guys will hear it because the speaker is implemented. There you go. Did you hear it? So I can actually... The funny thing was I had to remember how to program in BASIC. There you go. Okay, I don't know if we have any time for questions or if I'm around all. Okay, 2 or 3 questions if anyone has any questions at all about this insanity. Yes?
Yeah, why take all that nice data that you get from the Bosendorfer and then turn it into MIDI? Why not something more modern like OSC?
Well, I mean, MIDI is just sort of one of the things that I want to output. To be honest, I'm most interested in the raw Bosendorfer data. One of the things that I haven't done yet but plan to do is be able to take a particular note and look at the pressure contour of how it's played. And I think those pressure contours are going to be particularly interesting in some of the other churny stuff I wanted to study of just how hard are people pressing the notes and so on. And one of the things I'd love to do, I don't know if I'm going to have an opportunity to do this because I don't know anyone else that has the Bosendorfer piano that does this, is sort of do comparative tests as well, where get different people to play the same piece and then say, well, how are they differing in how they play it? But absolutely, I'm not interested in throwing away the data at all. MIDI is just one output, and I certainly want to do a lot with the raw data as well as convert it to other formats as well.
All right, thank you. Any more questions? I'll be here.
We don't want to start off running late, so.
Yeah, so what we need to do is we're going to be closing this room off for the talk.